Lesson number 15, daily summary. In this lesson, we tackle negative exponents, scientific notation, and roots. 1. Let's look at the pattern after filling in the right-hand column to discover why any number raised to the 0 is 1 and what is meant by negative exponents. So let's take a look at the right-hand column. I'll start here with 3 to the first. That's easy. That's just 3. 3 to the second going up this chain is 9. 3 to the third is 27. And 3 to the fourth is 81. And what I'm interested in is figuring out why in the last lesson I told you that 3 to the 0 was 1. A lot of students would say, well, if you have 3 to the 0, that means you have 0 copies of the number 3 multiplied together. So shouldn't that be 0, not 1? So right here, we're going to justify why 3 to the 0 equals 1 is a perfectly reasonable thing to define 3 to the 0 to be. And but let's just take a look at the exponents here. So I've got the fourth power, third power, second power, first power, 0 power, but the integers continue, right? -1, -2, -3, and -4. So let's talk about the right-hand side of this pattern here. So going up this list, 3 to get 9, we multiply by 3, and 9 to get 27, we also multiply by 3, and then 27 multiplied by 3 gives 81. So going up this ladder, multiply by 3 is clearly the pattern. Well, what if I wanted to go down the ladder? Well, it must be the opposite of multiply by 3, which is divide by 3. So 81 divided by 3, yep, that's 27. 27 divided by 3 is 9. 9 divided by 3 is 3. And if I want this pattern to continue, then I suppose I should just keep dividing by 3. And how much is this 3 divided by this static 3 over here? Well, it's 1. So like if I want this pattern to be true, then I have no choice but to define 3 to the 0 to be 1. And there wasn't anything special about the number 3. It's any number to the 0 would equal 1 according to this pattern. But let's keep going. We're just going to keep dividing by 3 as we go down the list here. So if I take the 1, the answer I just had, and I divide it by the same 3 every time, I just get 1/3. Okay, now it gets a tiny bit tricky. I'm supposed to divide by 3 again. I'll do this here on the side. 1/3 divided by 3. Well, maybe you've seen this before, but you can keep the first fraction, change division to multiplication, and flip the second fraction. So this 3 over 1 becomes 1 over 3 when you flip it over. And 1/3 times 1/3 is 1/9. So I guess that's what 3 to the -2 is. And now I think I'm starting to see a whole other pattern here. And that's that it's just a 1 on the top, and then this is a 3, and this is a 9. So I'm guessing this one's going to be a 27 with a 1 on the top. So let's write that. 1 divided by 27, and then 1 divided by, and then just multiply the bottom by another 3, and we get 81. And I'd really like us to come up with a way to figure out what 3 to the -4 is without writing down everything in this column here. But take a look at this 81 here. We have seen that 81 on this page. It is right up here. And so here is the new fact, is that if you want to know what 3 to the -4 is, you just put a 1 on the top of 3 to the 4. I'll say it again. 3 to the -4 is 1 on top of 3 to the 4. Likewise, if you want to know what 3 to the -2 is, it is just 1 on top of 3 to the 2. Or simply 1/9, and yes, in fact, that is exactly what our pattern told us. We're not going to get into it here, but it turns out if you have a negative exponent in the bottom, you can flip it up to the top and make it a positive exponent. So let's do our summary down here. Number 2, here's a useful shortcut for negative exponents. Negative exponents indicate movement. If you see a negative exponent in a numerator, make the exponent positive by moving the factor into the denominator. If you see a negative exponent in a denominator, make the exponent positive by moving the factor into the numerator. So here's how we rewrite this expression. 5r to the -9, d to the -8, all divided by 25r to the -5, d to the 3rd squared. So the first thing we need to do is apply one of our old familiar 5 properties to this piece, d to the 3rd squared. So hopefully we got that ripped off sheet in front of us. If not, go grab it. And what you're going to do is figure out which of our 5 properties this is, pause the video, come back when you've got it. So hopefully we see this is property number 3, and in property number 3 we multiply those exponents. So d to the 3rd, the whole thing squared, becomes d to the 6th. There it is. Everything else in this first fraction here has just been copied. Lots of good algebra comes from making one small change and copying almost everything. Copy everything else and make one small change. Okay, now we get to the heart of this new thing. I'm actually just going to write the answer even though it's typed down below. So I'm going to reduce my 5 and my 25. So 5 goes into both of them. So I'll put a 1 on the top and a 5 on the bottom. In fact, why don't we leave the top blank for now? But 5 over 25 reduces to 1/5. And then let's go ahead and move anything with a negative exponent in it. So for example, this r to the -9 has a negative exponent, and that means we move it. It was on the top, so it moves to the bottom. And in that very instant that it moves to the bottom, it becomes a positive exponent, r to the +9. Negative exponents mean move. Next up, d to the -8. Again, it's a negative exponent, so I move it. It used to be on the top. It is now going to find its new home in the bottom. And the moment you move it to the bottom, you make that exponent positive. Okay, everything on the top has been accounted for. Let's move to the bottom now. 25 has already been reduced. Next up is this r to the -5. It has a negative exponent, which means you move it. In this case, it was on the bottom. So we move it right up there and make it a positive exponent, r to the +5. And then finally, d to the 6th. D to the 6th has a positive exponent. The only movement indicator is a negative exponent. So don't go crazy and move everything. You only move the things that have negative exponents. So that d to the 6th has no reason to move. Just copy it right where it is. Okay, and now all of the exponents are positive, and this becomes a problem that we could have tackled last lesson. And so we're just applying our old familiar 5 properties. The only new thing here was to make the exponents positive. Okay, so let's look at the r's. In this case, r's divided by r's, that's our subtraction property, property number 2. I subtract 9 minus 5 and I get 4, and you put the r's where there are more of them. So let's write our answer down here. So r to the 4th downstairs, there are more r's down there to start, so that's where they end up. I see a 5 in the front, on the bottom, I put it right there. D to the 8 times d to the 6th, right next to each other again, that's one of our 5 properties. That's the first one. We add those exponents, now multiply, add d to the 14 right there. And I've written everything down, so it's really important that we bring in a placeholder on top. It is a 1. Gotta have a 1. All too often I see students who get to a problem like this where everything cancels and they write this as their final answer. And it's like, yeah, you got all the pieces, but you didn't acknowledge that they are on the bottom. And if there's nothing left on the top, then there is something on the top. It's an invisible one that you need to bring in. So that's our final simplified answer. And one of our new rules here is going to be that in any simplified answer, you are not allowed to give a negative exponent. Number 4, scientific notation allows us to easily work with very large numbers or very small numbers. We write numbers in this format by writing a number between 1 and 10 multiplied by a power of 10. Let's see it in part A. At this particular date and time, the U.S. national debt was approximately that number of dollars. Okay, so that number of dollars is hard to read. Is it millions? Is it billions? Is it trillions? Is it quadrillions? It's also hard to write. The person typing out all the zeros might make a mistake, right? You like omit a block of 3 zeros and all of a sudden you've changed the number quite significantly. So we're going to rewrite that number in a friendlier way for both the writer of the number and the reader of the number, and that's us. So the decimal point is currently way over here. It's invisible. And we are going to move that decimal point to some spot to make a number that is between 1 and 10. For example, if I were to put the decimal point right here, you don't need to write this, but this would give me the number 154.6 and then a bunch of trailing zeros that don't make any difference. And 154.6 is it's not that big a number in some contexts, but it is not between 1 and 10. We are striving to find a number between 1 and 10. For example, if I put the number right here, that would be 15.46, almost but not quite between 1 and 10. If I put the decimal point here, that gives me 0.1546. That's too small. That is less than 1. I need between 1 and 10. So the actual right spot, only spot to put that decimal point is right here, between the 1 and the 5, and we get 1.546, and then a bunch of trailing zeros that we don't need to write. Now this is much better for all of us because we didn't need to write however many zeros. I guess there are 10 zeros up there, right? We didn't need to write them, didn't need to read them, 1.546. But clearly 1.546 is not the same as this 15 trillion number that's up here. So we need to pay for moving the decimal point, and we pay for it by multiplying by a suitable power of 10. And the power of 10 is just how many spots you moved the decimal point. So literally, this is a matter of counting 1, 2, 3. Okay, so I guess I can do better because it's blocks of 3s, right? So 3, 6, 9, 12, and then one more, 13. 10 to the power of 13, and that's our answer. And we know that's right because we know that multiplying by power of 10 just moves the decimal point to the right. If you multiply a number by 10, that moves the decimal spot 1 to the right. If you multiply a number by 100, it moves the decimal point 2 to the right. If you multiply by 1,000, it moves the decimal point 3 to the right. If you multiply by 10 to the 13th, it moves the decimal point 13 places to the right. Part B. The diameter of a typical bacterium is about 0.000000241 meters, very tiny. So here's a number quite close to 0, and scientific notation is going to save the day again. First of all, when I typed this thing out, I made it friendly for the reader by putting a little space after every block of 3. I can't put a comma like I could for the 15 trillion number up above, but I can try to make it a little bit easier to read by putting those spaces. But let's use scientific notation. Again, the decimal point is currently here, and we're trying to put it in the one spot that gives me a number between 1 and 10. If you put it here, you get 0.241. That ain't it. If you put it here, it's 24.1. Nope. The only spot we can put it is right there. That's the only place that gives me a number between 1 and 10. So let's write that number, 2.41. No need to write the, we got like 6 zeros in the front, right? But you'd never write 0.00002.41. You just write 2.41. But again, we pay for it by multiplying by a suitable power of 10. So we are counting movements of the decimal point. It is tempting to say, oh, 6 zeros, put a 6. That is not correct. We are not counting zeros. We are counting movements of the decimal point. So in our case, we moved 6 spots there, but then one more spot there. So 7 is our power of 10. 2.41 times 10 to the 7th. That is in scientific notation. Unfortunately, that is not the diameter of a bacterium because 2.41 times 10 to the 7th is very big, right? 10 to the 7th is what, like 10 million. So that is not it. And the way that we say go the other direction is to put a negative exponent. 10 to the negative 7 moves the decimal point 7 places to the left. So how are we supposed to know this? Well, let's see. So 10 to the negative 7 we know means 1 divided by 10 to the 7th, which just means divide your number by 10 to the 7th. So that's why the decimal point goes left and not right. But I don't want you to memorize, like negative goes left and positive goes right. I think it's really easy to get those backwards. So all I need you to know is that 10 to the 13th is a really big number, and 10 to the negative 7 is a number very close to 0. And that's all. So just say to yourself, positive exponent corresponds to the large numbers. That's something very familiar to you from way before this class. The new thing for this class is negative exponents, and 10 to a negative power gives you a number close to 0. And that's how I can tell whether I want a positive exponent or a negative at the end of the day.